Has genetic entropy been refuted? Critics have claimed that the theory has been answered. Papers have been published, simulations have been run, and counter arguments have been offered. Yet here we are in 2026, and the challenge remains. If slightly deleterious mutations accumulate faster, then natural selection can remove them. What does that mean for the long-term history of life? More importantly, have critics actually demonstrated a solution, or have they merely assumed one? Join Paul Price, Sam, and myself as we leave no stone unturned here tonight in examining the latest objections, responses, challenges, and evidence surrounding the topic of genetic entropy. If the problem has truly been solved, to the critics, prove it. If not, the implications for common descent and human origins are profound. Sam, my award-winning co-host, and Paul Price, the genetic entropy debate champ. It's great to have you, brothers. Before we hand it to Paul, Sam, let's start with you. How you doing? And do you have any words of introduction for us?
Yeah, hey, thanks for having me on. I'm looking forward to having this conversation and listening to Paul kind of recap his epic taking this topic on head on in debate. And so, yeah, I'm excited for tonight's show.
So am I. One of my favorite topics. And critics will posture, they'll talk a big game online, they'll assert that genetic entropy has been refuted. But Paul, a couple questions. How you doing today? Secondly, has genetic entropy really been refuted, brother?
I'm doing great. And as I say every time you bring me on, thank you for asking me to come on. And it's a blessing to get to address you and your audience and Sam to fill a need, I think, that for some reason, and this is humbling because I don't know why it's specifically me that is filling this need. It's a little bit surreal, to be honest, because I'm not a professional scientist, and I never have been a professional scientist, but somehow through God's, purposes and design and fate and whatever you want to say, I have been thrust into this position to be somehow one of the foremost defenders of John Sanford's genetic entropy out there. And again, I don't think it should be that way. I feel kind of bad because Dr. Sanford's work deserves a lot more recognition than it gets. And that includes within the professional creationism or creationist community. It's underutilized as an argument. It's underappreciated for its power. Dr. Sanford's work is underappreciated. And so I feel like more people need to be, touting this for what it is. Because, at the end of the day, Darwinian evolution is supposed to be science, right? And it's supposed to be reality. And there's supposed to be some kind of underlying real life genetic mechanism that makes it possible to turn, Donnie, what is one of your many phrases? Protists into philosophers. I don't remember them all now. There's so many of them, but
fish to fisherman, bacteria to biologist.
Fish to fisherman, whatever you want to say. There's supposed to be some underlying process that makes this possible. And if you want to call yourself an intellectual in any way, you're supposed to be able to pull back, the curtain. You're supposed to be able to look under the hood, and you're supposed to be able to see something that makes any sense at all. And unfortunately for the evolutionists, you don't find that at all. When you look under the hood, what you find is genetic entropy. When you look at population genetics, which is, a tiny niche field in the overall scientific community that I think is poorly understood even among professional biologists. And Dr. Sanford says that in his book, by the way. But these are the specific scientists that are supposed to have a handle on this. And when you read what they write and when you pull back the curtain, you find they don't. You find there is no mechanism. And in the words of Dr. Maisel, Dr. Joanna Maisel of the Maisel Lab, fitness keeps declining no matter what. That's the reality. I'll say that again. I'm quoting the Maisel Lab, which is, as far as I know, the only genetics lab in the whole world that is, devoting major effort to solving the paradox of genetic entropy, or Kondrashov's stochastic mutation load paradox, if you want to use the most technical term. Yeah, that's what the Maisel Lab says. They said, fitness keeps declining no matter what. And you know what? When you use biologically realistic parameters and you use the simulation tools that we have, I honestly, any good one is going to show this to you. It used to be all about Mendel's accountant back in the day, and I missed out on Mendel's accountant. I never got a chance to use it. For the longest time, it wasn't publicly available. And obviously, it's been heavily maligned by the evolutionary community. I don't think with good reason. But anyway, now we have SLIM. And SLIM is a similar type of forward simulating, mutation program that is going to allow us to do essentially a very similar thing, if not the same thing, as Mendel's accountant. And the advantage to using SLIM is that both we and our opponents can collectively agree that this is a realistic simulator that hasn't been rigged in favor of creationism. So, whether it's fair or not to Mendel's accountant, the claim is out there that it's rigged. Again, I don't think it is rigged. But hey, let's just give them, for the sake of argument, let's say, okay, I'll use your simulator, Dr. Hancock. So to take you back to the origins of this debate, Donny, you and Sam, I believe, have heavily interacted with Zach Hancock and Daniel Stern Cardinal over the past several years. And it goes back, I think, all the way back to when I first started interacting with Dan Stern Cardinal was on Reddit back in 2019, which is a time when I was trying to drum up information that I can use for writing articles about genetic entropy to see what the educated adversaries to Dr. Sanford's hypothesis, what they had to say. And so that was my origin with him. But later on, I heard about Zach Hancock, and I found out that actually it was you and I, Donnie, that actually stirred this up when we did a stream that was responding to something that Zach Hancock had put out attacking John Sanford. And we mentioned a paper that John Sanford had published with Baziner. And apparently this was Zach Hancock's first introduction to this paper from our web stream. And in his words, he was motivated by rage and spite to want to do something to hit back at Dr. Sanford in the literature because he had gotten this published. And in fact, he even, Donnie, I don't know if you were aware, he even put both of our names in the acknowledgments of his paper.
Yeah.
So it's very funny.
An honor.
Yeah, it was an honor. And that's probably the only time I'll be in the acknowledgments of a paper. I don't know, but it's funny in any case. A little bit cocky because, especially in retrospect. And if you go back to the stream that he and Dan Stern Cardinal did after that paper got published, I'll show you what I'm talking about. This stream right here, it's back to the fundamentals, a reply to Baziner and Sanford 2018. This is on Dan Stern Cardinal's channel. And this was their kind of triumphant, we beat the creationists sort of victory lap stream, if you want to put it that way. And the important thing from that stream, I think, was that toward the end, they started talking about their simulation. claiming that it had overturned genetic entropy. And Dan Stern Cardinal gave us the target. He said, and his words were, creationists, this is your homework. These are your parameters. If you want to prove genetic entropy is a real thing, you need to defeat these parameters that we used in our paper. Now, for
Right.
those of you that aren't following all of this, what they did in that paper, they allegedly created a simulation that showed, using what they claimed were realistic biological parameters, that genetic entropy didn't happen. Fitness didn't decline. In fact, he claimed that, the fitness went up to a carrying capacity. Now, the interesting thing is that he specified in the code, he specified a carrying capacity. And the way it was done was using fitness scaling, which means that as the population goes over the carrying capacity, fitness gets artificially docked. It gets artificially brought down by the amount that it's over, or as a function of the amount that it's over that carrying capacity. The idea being it's supposed to make the population stop growing at that point. But the funny part, and one of the things I showed in the debate, is that their sim was so wildly unbalanced that, in fact, it shot to the moon. It never stopped. The carrying capacity just had no effect. It just kept on going and going. And the reason for that is that it was so horribly unbalanced with the ratio of deleterious to beneficial mutations, and also with the proportion of his distribution that was actually open to selection. So, and one of the things that I think would be good, Donnie, is if in the description of this video, you could kind of put a timeline of these uploads. The very first one that people need to watch is the genetic entropy open debate that I did with you on your channel several years ago.
Yep.
Because that's where I kind of took people through the very nuts and bolts basic, here's Dr. Sanford's book, here are the exact analogies that he used. You know, I put a lot into that to try to make it as approachable to the layperson as possible. So that is a really good place people should start. Unfortunately, right here, we're in like the most nitty gritty weeds of it. And that's good. But for people out there that maybe don't understand what we're talking about right now, this is where they need to go. Genetic entropy open debate. I want to say that was maybe 2023 or something like that, maybe 2024. But that's a good starting place. But in any case, what Dan said in that stream was, here's your target, creationists. This is what we're daring you to attack and show is wrong. And in the debate, that's exactly what I did. I absolutely showed it to be wrong. Let me just very quickly bring up a couple slides here. And I'm not even going to put it full screen, but basically, you know, what I did was I said, this is Dr. Kondrashov. He realized this problem in 1995. And actually, he's not the first one. Dr. Kimura, who is one of the founders of neutral theory, along with Tomoko Ota, he put out a paper in 1979 where he acknowledged the problem as well. And the rescuing device that he used in 1979 was mega beneficial mutations. And ironically, the field has tried a million options. They've all failed. And that's back where they're at right now. That's what Dr. Maisel, among other things, that's what Dr. Maisel is trying to look into now. Mega beneficial mutations. And it's a dead end. But this is where it started, 1979 Kimura. Let me go down here. Distribution of fitness effects, guys. This is talking about all of the possible mutations that can happen in the population, looking at the effect that they have on fitness and graphing that together with their probability or their frequency. And that center area is called, in Sanford's original book, it was called the no selection zone. Now, this is an area where they tried to muddy the waters in the debate and they attacked his wording there. Technically speaking, there is selection. It's just that selection is so weak that it is overwhelmed by drift. And so if you read Dr. Sanford's book, it's clear he understands that. He was using this phraseology, but they tried to make much of that. If you would prefer, you can call it the effectively neutral zone, and that would be more maybe technically correct to call it that. But essentially, this is the zone of mutations where random drift is a much larger factor, to the point of totally drowning out any selective effect that individual mutation might have. And so this area, the shaded region, is the problem. This is what creates genetic entropy. And it also turns out to be the Achilles heel of Zach Hancock and Daniel Stern Cardinal's simulation that they did, because I actually ran the numbers. I called their bluff. And I looked, let me see if I can find the slide. Here's where I ran the numbers. If you look at the percentage of their distribution and their simulation, it only contains about 2.5% of that no selection zone or effectively neutral zone compared to all the rest. Now, we know that is highly, highly unrealistic. In fact, most mutations fall in that effectively neutral zone. So this is right here an immediate downfall for the simulation, and why it's not accurate, because they did not include the exact thing that causes genetic entropy, which is mutations that are unselectable. They cannot be weeded out or purified out of the population. So basically, those two things, I think they used a 100-to-1 ratio of deleterious to beneficial. In reality, it should have been 1,000-to-1, even according to the paper that they cited, which is the San Juan et al. Paper. So they used far too many beneficials, and on top of that, they hyped up the power of natural selection artificially to cause it to weed out all the deleterious. So when you do those two things, naturally, you're not going to see genetic entropy in action. And so that's all there was to that. It wasn't, at the end of the day, that wasn't the hard part. The hard part was I ran my own simulation that I do deem to be accurate. In fact, I would deem it to possibly be the most accurate simulation of mutation load in humans that has ever been put forward. And the reason I can say that is that basically in the professional world, the academic world, the population geneticists that work on this apparently don't bother publishing such things because it doesn't help them. It doesn't look good for them. It doesn't show evolution happening. It shows fitness decline happening. So, I guess what's the point of publishing it? I don't know. I'm not sure why we don't see these types of things published, but it is common knowledge. And again, go back to the Maisel Lab's own website where they admit this. They admit that not only do they know that fitness keeps declining, but they deliberately avoid the problem in their publications. So, there's so much that has been admitted here. The last thing I'll say before I turn it over to you guys to ask some questions or move the discussion however you would like to move it. The last thing I'm going to say is that after the debate, so during the debate, there were lots of interesting things that were said, but perhaps the most interesting things of all happened after the debate on the Peaceful Science Forum, where basically Zach Hancock has been forced to admit that I was right about basically every point that I made in the debate. And that is astonishing. I don't think I've ever seen that happen before. But, he has admitted that his simulation is not relevant to Kondrashov's paradox. Now, he continues to claim that somehow Sanford's genetic entropy is I don't know. I don't understand how he can justify claiming that they're separate. So, I mean, Kondrashov's paradox is the biggest part, or at least a very major part, of what Dr. Sanford refers to as genetic entropy. So it's really, I think, telling that that Hancock has put out all these videos over the years bashing Dr. Sanford, bashing creationists, and then at the end of the day, when push comes to shove, he doesn't seem to know even the basics of genetic entropy, even though he's put out countless videos on it, and he claims to be surprised that genetic entropy is about Kondrashov's paradox. It's baffling, and I can't quite understand why things went down the way they did, because I would have expected a different showing in that debate. I certainly would have expected Dr. Hancock to defend his work that he's got out there published in the literature. And it's still a head scratcher that didn't happen in the debate. And but guys, I don't want to just keep rambling. What points would you like to cover? Or perhaps what points would the audience like us to cover?
Sam, did you want to start, or myself?
Yeah, sure. No, so you kind of did answer it. I was going to ask you. I did speak with Zach. He's a lot easier to speak with than Dan. And I asked him specifically if he believes he has refuted all forms of genetic entropy. And he wasn't willing to answer that directly. Instead, he began to challenge my nomenclature, my words that I was using. He was very adamant that he had refuted Dr. Sanford, but I also pointed out to him that Dr. Sanford is citing secular population geneticists. So, yeah, I mean, I was wondering if you could tell me what he thinks the angle is there, how he's overturned Sanford without addressing the broader picture here.
Well, one thing I have repeatedly noticed from Zach Hancock, and this isn't unique to him, this is something I believe, honestly, professional evolutionary scientists kind of get trained in this skill, if you will, of doublespeak. And unfortunately, it's an effective tactic to kind of muddy the waters when you don't want to come out and admit something openly. But what I'm saying is doublespeak. When he claims that he's refuted Dr. Sanford, but then on the other side of the token, he claims he's not solved Kondrashov's paradox. Well, yeah. You can't have those, both can't be true, because Dr. Sanford is talking about Kondrashov's paradox in his work. So to claim that you've refuted Sanford is a claim to have solved Kondrashov's paradox. And in his paper, he claimed to show that fitness did not decline using realistic parameters. Well, if that's the case, that would be a solution to Kondrashov's paradox. But he's in writing publicly saying, no, he is not. And he said it in the debate. He said, no, I have not solved Kondrashov's paradox. Now, in the debate, he said, no, I haven't solved it, but it has been solved. After the debate, he corrected himself again, and he said, oh, I shouldn't have said that. What I should have said is, we have solutions. So now what is trying to be said here? He hasn't solved Kondrashov's paradox, so I guess you can throw that paper right out. He's not even standing by it. And then he initially claimed that others had solved it. Now he's saying that was wrong as well. He shouldn't have said that. Instead, he's saying we have solutions. So basically what he's being forced to admit is it's unsolved, but there are attempted resolutions, is the best they can say. So you have to force them to admit these things through gritted teeth. But at the end of the day, they have not solved the paradox of genetic entropy.
If I could ask this, and we have a lot to ask based on your opening words there, Paul, so we'll try and touch on everything. But to kind of back up a little bit to the details of Zach and Dan's paper, because I think it's important. Over the last couple of years, we in the creationist community, those that have studied genetic entropy extensively, especially, will bring up genetic entropy. The majority of critics, the cheerleaders of people like Dan, they don't really have a good rebuttal to when we press the problem of nearly neutral, slightly deleterious mutations accumulating. Selection can't see the majority of them, and so they spread and degenerate. They won't have a rebuttal, but what they've done over the last couple of years, Paul, is they'll just cite Dan and Zach's paper. Oh, this has already been dealt with, even if they don't really understand what the paper is saying. They just cite the paper, post the paper, mention the paper, and they feel like they've won the debate for some reason. So obviously that's been a big talking point over the last couple of years. So going to the debate, you address the technical paper that they published extensively. There's a couple questions I have on it. So you had mentioned in the debate, and I just rewatched the debate. That was, I think, my second rewatch, and then I moderated it. So I got to experience it live. Excellent debate. And so a couple of the points, beneficial mutations. Can you reiterate or clarify a couple things? Do they assume unrealistically, you in the paper using their simulation, too many beneficials as compared to reality? How many beneficials would come about, the average, but also they underappreciate the nature of effectively neutral mutations? Those 2 points, effectively neutral mutations and beneficials, are they arguing in that paper basically in a way that puts too many beneficials in the simulation and then also not enough effectively neutral mutations, Paul?
So it's all of the above, of the above. So the ratio of beneficials was 10 times more than it should have been.
10 times more.
Yeah. If they would have read the paper that they cited, the San Juan et al. Paper, they state in the paper, it is widely acknowledged that the ratio should be 1,000 to 1. Now, I'm skeptical of that for large creatures like human beings. I bet it's worse than that. Right. But okay, we're going to give it to him on that, okay? We'll say, fine, 1,000 to 1. We're going to take your consensus view and use it. But that's not what Hancock did. He used, he used 100 to 1. So, no, it was way too many beneficials. 100 to 1 is ridiculous.
Paul, if I could play devil's advocate, maybe help me understand what his response was. It was in the Q&A. I don't now, because I moderated it, I'll stay neutral in light of the debate. You both did a great job. It was a great debate. I won't say who I thought won or lost. I'll just comment on aspects of the debate. But I will admit, genetic entropy has not been refuted in general. Okay. And that's why we're doing this program. Leave no stone unturned, right, gentlemen? So Paul or Zach in the Q&A, if I remember correctly, he had said, well, in counter response to the beneficial argument, well, the beneficials had such low effects, I think he said, in the Q&A. So it doesn't really matter. He acted confused when it was brought up. As a matter of fact, one of Sam's questions was AI and compensatory mutations, which in other words, they've got too many compensatory or beneficials. And he disregarded that. So Paul, do you remember his response there? And what would be a good way to address that?
I mean, that was one of the shocking moments of the debate when Zach admitted he didn't realize that his simulation didn't have effectively neutral mutations. I would have thought he would have, if he were someone who understood genetic entropy, that would be the very first thing to make sure you're modeling. Right. Is effectively neutral mutations. Mm-hmm. So the fact that he didn't model that and then also said he didn't realize that he didn't model it, that's a head scratcher. That should not be. You're putting forth a paper where you claim to be refuting genetic entropy with a simulation, and you forget to include the one thing that causes genetic entropy, which is the effectively neutral mutations. That's a major oversight. Right. It's such a major oversight that it raises all kinds of questions about what was going on in the process of getting that paper published. I want to say this. Was he missing your point? Because in the Q&A, this was a huge part, and you just addressed it in your opening words with Sanford, the no selection zone.
And I like what you said, the effectively neutral zone, essentially, if you want to be technically accurate. And Zach was pointing out, but you would admit that not every single effectively neutral mutation is unselectable. But you've pointed out, well, the point is the vast majority of them are, that it's negligible. It doesn't change anything. Is that an important point that people miss? Because there was some rhetoric after the debate and during the debate that it's like, well, now they're shifting from no selection zone to mostly no selection zone, Paul.
So this is kind of a complicated concept. And by the way, Donny, you are breaking up a little bit on me. I don't know if it's you or me, but
Okay.
Sam, are you seeing any of that? Is Donny breaking up for you?
No, he's looking fine, and the sound's coming through just fine on my end.
Okay, and same for me. I'm good also.
Yes.
All right, so it's just ignore that. We'll move on. Before we get too far away from this, I'm going to mention one other thing about the parameters. Okay, they used 100 to 1. However, guess how many mutations he had per individual per generation? Now, humans have, realistically, we have anywhere between 72 to 100 per generation. Yeah. And Donny, I know you've cited that before. How many do you think he modeled in his simulation per generation?
Half that.
Try again.
A quarter that.
Try again.
Wow.
One mutation.
Well,
one mutation.
So
one new mutation per individual per generation. Now, when your distribution is almost all selectable, the probability that one mutation is going to be effectively neutral is minuscule. So obviously, it's not going to be able to overpower the effect of natural selection. It's just, it's baffling. The simulation was baffling when I really looked down into it. I could not understand what they were trying to do because everything was so far off. But okay, here is where it gets a little bit tough to explain. When you're talking about, and by the way, he pulled a stunt, and I'm going to call it a stunt because he pulled out those not even distributions. What is the right word for what he had? Basically, allele frequency graphs over time. And he pulled them out of nowhere in the 5-minute cross exam. He didn't make it clear where he got them from. At the time, I assumed he was pulling them from some kind of published work somewhere. And I should have called him on it, and I didn't. So that was my bad there. But it turns out that those graphs were graphs that he personally created with a simulation that he personally did. It didn't come from any peer-reviewed literature. And he didn't make public until after the debate, after I called him on it. He didn't make public the code that he was using to create those graphs. So it was highly misleading what he did. And I think he was just trying to give me an opportunity to say a soundbite that could then be taken out of context, which is exactly what Dan Stern-Cardinal did after the debate. He created a video and he said, look, right here, Paul conceded the debate. He admitted that there's selection. Okay, that was never under debate. So it was a complete red herring and a complete misdirection all around. Zach should have been spending those 5 minutes asking me questions about what I presented. Instead, he tried to pull this stunt that I think ultimately just backfired because it has nothing to do with the debate. Allele frequencies are stochastic. Allele frequencies change randomly over time. And one of the things that Michael Lynch even brings out is that when you look at individual pathways of allele frequency changes over time, it can be really hard to differentiate between random drift and selection because the two could look identical theoretically, especially with small sample sizes. And that's what we had in those simulations that Zach Hancock did. We had small sample sizes, but he wasn't even using SLIM. What he had said prior to the debate is that the best program to use was SLIM. And then during the debate, he didn't even use SLIM, and he didn't even defend his work. It was really bizarre. But basically what he was trying to get at was, okay, an effectively neutral mutation still might have a trajectory over time that is slightly off from purely neutral. And fine, we can grant that. But that's not the point, because even if it's slightly off from purely neutral, it's still not off by enough to matter. And that's why Kondrashov's paradox happens in the first place. And if you put the correct parameters into SLIM, SLIM will show this to you. That's what I did. And guys, if you want me to show you the slides where I actually show my simulation in action, I can do that. But basically, it's important that people understand the mechanics of genetic entropy, especially since before I was doing the prep work for the debate, I didn't fully understand it myself. So I was personally helped by the process of doing this debate and using SLIM. But yeah, guys, what are your thoughts on that? What do you think?
Yes, I would like you to present those slides, because especially for anybody who hasn't yet seen the debate, or maybe they only watched it once, as somebody who's gone through it a couple more times, you get more out of it each time you listen to it, because there's a lot of technical information there. A question before you share your slides, because your simulation is through SLIM. What's the difference between Mendel's accountant and SLIM? What are the pros and cons? Now, I heard you say earlier, well, because there's a lot of criticism of Mendel's accountant that pro-creationist parameters are baked in, or maybe it's rigged basically to give creationists the results that they want. So let's go with SLIM, because that's what Zach uses, that's what Dan uses. So let's kind of use their own tool to show why they're wrong. Or is there any true differences, Paul?
I honestly, to be honest, am not well educated enough in that question to give a good answer. So I'm not going to try to say what are all the differences between SLIM and Mendel's accountant. I absolutely don't believe it's rigged. I mean, that's just that's a ridiculous allegation. Dr. Sanford is one of the most upstanding people I've ever seen. He would never do that. He would never rig a piece of software to falsely confirm his results. So that's just a slander against Dr. Sanford to say that he's using rigged software. It's certainly not rigged. But which is better, Mendel's accountant or SLIM? I don't know. Mendel's accountant is older, I believe. I think SLIM came about more recently. That doesn't mean it's better. I'm not sure. But in any case, I avoided that issue because I did not, at least at the time of doing this, I'm not familiar with how to use Mendel's accountant. And I was able to figure out how to use SLIM, so I just used it. But I'm not saying SLIM is necessarily better.
Before I ask the next question, Sam, let's just test your mic real quick, because there was a bit of an echo when I had you unmuted and Paul was talking at the same time. So if you have to adjust before Paul shares his screen, then we'll do so. Paul. Yeah. Okay. So I do hear the echo. So maybe, but I don't hear it anymore.
So I have a mute button on my mic. I can adjust something over here. So let me do that for a little bit here, and I think I can get rid of it.
Yeah, feel free to play around with that. I got you at 80 volume, and I do have reduced mic background noise on, but maybe you can, because it was good at first. So Paul, I'll ask this, and then let's give the audience what a lot of them I'm sure want to see. I want you to go through those slides in your simulation. And there's a couple questions that came in that I think you going through those slides will help to answer, or at least set the foundation to answer. Has there been any, after this debate, a couple questions. Do you feel that Zach defended their paper in the debate? Secondly, has there been a defense of their paper and a refutation of your simulation post debate, because I know earlier you were talking about peaceful science, and I went through all of those. There's a lot of comments there, and there's a lot of, and you're taking them all on like a superhero. So a good for you. It's like 10 on 1. That's why before we went live, I said Dr. Price, because you've earned it, brother. So yeah, a couple questions. Did Zach defend his paper in the debate, and has there been a defense post debate?
Okay, so no to both, at least with respect to Zach Hancock. He did not defend his paper in the debate. I would encourage everyone to watch the debate. There's no point in the debate where he barely ever mentions anything about his paper. Only when I force him to talk about it does he talk about it. And he certainly is not able to defend it whatsoever. And afterward, he has gone on record and stated that his simulation, in fact, I'm going to quote him word for word so I can't be accused of anything here. Here are his words in the Peaceful Science blog. If genetic entropy equals Kondrashov's paradox, as Paul plainly states, then these simulations are irrelevant. Those are his words. So he has admitted his simulation does not solve Kondrashov's paradox, which in turn means it does not refute genetic entropy, period. And apparently we all agree on that now. So it seems like we can put his paper behind us from this moment forward.
Is the nicest way to put it.
Yes. Yes.
On that issue, at least. So
Yeah.
it's
Now,
not. Oh, good.
Go
Paul,
ahead.
go ahead. Go ahead.
I will also say he has not, as far as I can tell, Hancock has not attacked any of the parameters that I used in my simulation either. And that's because he has turned to a totally different school of thought. And he is basically what I would describe it as, you're losing at a game of chess. So you just, you throw the board down and you say, let's play checkers. That's what's going on here. He's not playing by the same rules. He's appealing to a completely different concept now, which is called the infinitesimal model, he calls it. But really, he's basically, where he's getting his stuff from now is from Charlesworth, a 2013 paper by Charlesworth. And that paper has also been responded to. In fact, Dr. Sanford himself has responded to Charlesworth's paper in the updated version, I think the 2014 update edition of Genetic Entropy. And I'm just going to read out what he says, because this is not something that's easy to find on the internet if you don't happen to have this book.
Is it in his book here, Genetic? I wonder if this is the updated version.
That could be the updated version. It's on page 116. Donnie, if you turn to page 116, you might see it.
And you can feel free to read it out, and I'll see if I got it.
I'm going to, yeah.
Oh, I do see it. Yeah, the two papers by Charlesworth.
Yes.
Yeah.
So he says the two papers by Charlesworth and Lesquet et al. Begin by clearly establishing that population geneticists really do have a very major theoretical problem associated with deleterious mutation accumulation. They then set out to try to solve that problem. Unfortunately, they formulate the problem in the context of traditional genetic load calculations, which are poorly correlated to reality and which require a long list of unrealistic simplifying assumptions. Both papers follow the long-standing tradition of trying to force-fit complex population dynamics into a few oversimplified algebraic formulas. Their papers do not actually explain how selection might eliminate deleterious mutations as fast as they accumulate. Instead, they skirt and here's the important part. This is probably the most important sentence to keep in mind with respect to Charlesworth. Instead, they skirt the primary issue, accumulation of genetic damage, by deliberately clouding the definitions of fitness, mutation effects, and selection. In this way, the genetic entropy problem seems to disappear in the resulting cloud of ambiguity. And that is what Charlesworth's paper does. it appeals to something that he calls stabilizing selection instead of purifying selection. Well, remember, in order to avoid the problem of genetic entropy, we need to purify these damaging mutations from the population. We need to get rid of them. Charles Worth says, well, we have this other concept called stabilizing selection, where we're, and this is something that Zach latched onto, and Charles Worth did this. He talks about, well, we're going to talk about a trait, and we're going to say that selection can act to maintain an optimum trait even as other things change. Well, that's really not the problem that we set out talking about. That's not Kondrathov's paradox. It's a whole different issue. And so it is not a solution to Kondrathov's paradox at all. And that's probably why Dr. Joanna Maisel states on her website that we still don't have an answer to Kondrathov's paradox. Surely she's aware of Charles Worth's paper from over a decade ago. From 13 years ago, this paper came out. I'm sure Dr. Maisel is aware of it, but she does not consider it to be a resolution, nor should anyone else, because it's just basically talking about a totally different concept. And that's kind of the weird thing that Hancock himself did in the debate. He started talking about corn oil and, the agricultural industry artificially selecting for beneficial traits. None of that stuff has anything to do with genetic entropy, but I guess it plays well with an audience that doesn't understand the topic.
Well, that's incredible that, okay, every time they keep going back to the drawing board and then we look into their argument or the paper that they want to cite, it's addressed. And so at this point now, some of the critics, Zach in this instance, has moved backwards into the past and pulled out a paper rather than defending his own paper in the debate and post-debate. He's latched onto a paper from years ago that Dr. Sanford himself has already responded to, right, in Genetic Entropy, and quite thoroughly as well, as I followed along with you. That's incredible.
Exactly.
Wow.
It was odd. An odd decision, to say the least.
Do you think perhaps he was relying on you maybe not knowing about it, and so he could score some points there? Since I'm sure he assumed, and Dan has assumed, that you're going to be spending most of your time focusing on their paper, since that's what's being passed around over the last couple of years as the defeater of genetic entropy. And so to go back into the past and go to an obscure paper like that, I'm curious as to your thoughts, Paul. Why choose that paper even though Sanford's already addressed it years ago?
Well, he probably wasn't aware that Sanford had addressed it, first of all, because it wasn't in all versions of his book. So it may not have been in the version of the book that he read. I don't know. I don't want to go too far into, assuming whatever his motive might have been, but I will definitely say it was a bizarre choice not to defend his paper. I don't know if it's, like he said it's irrelevant to Kondrathov's paradox. So, it's possible that he came to that realization on his own before the debate and realized he needed to change gears. I don't know.
Right, because he did say in the debate that because you asked him in the cross exam, have you solved Kondrathov's paradox? Has your paper solved it specifically? And he said, if I remember correctly, just paraphrasing, he said, no, but our paper wasn't trying to. They were basically trying to mimic Sanford's paper and Basner's. And so I want to ask you this, Paul, with your simulation, and perhaps we'll start shifting towards your slides and going over the results of your simulation and the details on it. Are you confident to say that your simulation, as compared to the simulation that Zach and Dan ran, actually has realistic numbers in terms of beneficials, effectively neutral mutations, DFE, distribution of fitness effects? This all matches the biological world and what the technical literature says about these things, like how frequent beneficials would be, as compared to Dan and Zach's simulation?
I will say confidently, yes, I do believe it's accurate. In fact, I've put it out there I've been putting it through the fire at the Peaceful Science.
Yes, you have.
You know, and the only thing that anybody there has been able to say about it, there's been basically 2 different people that have tried to respond to my work. And I'm not going to include Hancock in that list because he's not one of them. One of them is a guy named Rum Racket, and I don't know how to pronounce that name, but Rum Racket. His attempted solution has to do with epistasis, various types of epistasis that he claims are going to rescue it. Specifically, he appeals to diminishing returns epistasis. Now, the problem there is diminishing returns epistasis tells us how fitness stops increasing. So in certain lab environments, you can see, and there are papers that have seen where when you have a strain of bacteria or a virus that is not accustomed to your laboratory conditions, you can see a short-term period where fitness increases to a certain point as that strain of bacteria or virus acclimates to your lab setup and gets better in that setup. But there's always a limit to that. And that's why it's called diminishing returns epistasis. There's a limit to how much better they can get when you put them into that new lab environment. So diminishing returns epistasis tells us why or how, or at least talks about, I'm not even sure it tells us exactly how, but it talks about how fitness stops increasing. Now, what genetic entropy is about is how fitness keeps on declining. So it's the exact inverse of that. Fitness isn't increasing, it's declining. So when this gentleman appeals to diminishing returns to explain that, he's turning reality on its head. Diminishing returns doesn't tell us how fitness stops declining. It tells us how fitness stops increasing. So that's the first person that tried to attack my simulation. He didn't offer any parameters that were any better than mine. He just claims that there's some type of thing that's happening totally outside of what we are able to model in SLIM, where over time the distribution of fitness effects is going to change. And you're over time, allegedly, according to him, you're going to start getting more and more beneficials as the fitness goes down. The problem is there's no reasonable explanation for why that would happen. And diminishing returns epistasis doesn't give us any answer to why that would happen. It's the exact opposite. The other individual that had tried to attack my simulation was Dr. Joe Felsenstein, who is, I am told, a very famous geneticist. According to Hancock, one of the most famous population geneticists. So it's amazing. The only thing that Dr. Joe Felsenstein was able to say against my model was that he brought in junk DNA. And he tried to claim, well, your mutation rate is too high. It should be 10 times less because all the mutations that would fall in junk DNA, according to him, will just have no effect at all. Which I don't think is the least bit realistic. And junk DNA is a dying concept, which is being increasingly falsified. But you know what? I granted him that. And even if you grant them junk DNA, it still doesn't solve the problem. It still doesn't rescue anything.
So even with junk DNA, so are they stuck between a rock and a hard place? Because you're saying even with junk DNA, the mutation rate is still high, too high?
Yep. Even with junk DNA, the mutation rate is still too high, and there's still too many effectively neutral mutations. You can look at the work of Eyerwalker and Wolfit. They published a DFE for specifically humans on non-synonymous mutations, which means mutations that occur in the coding region and they change the expression of an amino acid. So with amino acid changing mutations, these are going to be the most impactful class of mutations of all. And even that class has a sizable proportion of effectively neutral mutations. And so, no, even if you grant junk DNA, it still doesn't solve the problem. But those are the only two people that have had anything to say about my simulation. Hancock never had anything to say about it.
Wow. So now, so it isn't just, hey, my simulation can beat up your simulation, assertion wise, right? We often like to point that out in our theology debates when people start arguing from church fathers. My church father can beat up your church father, because anybody can quote anything. No, what you're saying is your simulation is superior. It outclasses their simulation because it is based on what we know about the real world. It has an accurate distribution of fitness effects. It accurately simulates the number of beneficials that would, at the end of the day, I wonder with the beneficials that they think would pop up and help to counterbalance or drive adaptive change. Are they assuming that, this is me just kind of thinking out loud, I don't know if you're going to know the answer to this, but are they assuming that those beneficials are non-reductive? Because we talk a lot about here that even when beneficials pop up, oftentimes when you look under the hood, Paul, you mentioned earlier, let's look under the hood, look at the genotypic effects. It's due to degradation, the breaking down of certain systems, like sickle cell anemia, right? Broken cell, broken protein. Okay, there's a small benefit, but it's reductive. So I don't even see how reductive mutations would help to counterbalance.
Well, I agree. And when you look at these diminishing returns situations, I think in most, if not all cases, it turns out to be reductive. However, this is the important part. You don't have to grant that. I mean, you don't have to die on that hill to show genetic entropy. You can grant that mutations will occur that are beneficial and non-reductive. The problem is still there because there's not enough of them.
Right.
Okay. That's the problem. There's not enough. Even if you grant them non-reductive beneficial mutations, you're not going to get enough of them to counterbalance. And the whole idea of counterbalancing doesn't make sense. So Dr. Sanford talked about it in his book. I used in my presentation, in the Genetic Entropy Open Debate presentation, I used the analogy of the red wagon, and it was a red minivan. And I showed how the minivan was degrading all over with rust, all over the van, right? All parts are degrading homogeneously with rust. And then you take and you put a big spoiler on the back, right? And this is your beneficial mutation. Okay, how does that change the fact that the rest of the vehicle is rusting out?
Yeah, it doesn't change it at all.
A mega beneficial mutation does not have the ability to counteract the damage that's being done.
It's like if I had a car, I mean, we all have cars. We're supposed to get regular oil changes. We're supposed to change our tires once in a while, our windshield wipers, fix certain dents, and even try and fix a rusty hood. But overall, you're not preventing the overall degradation or destruction of the car. No matter how many oil changes and no matter how many times you appropriately change your tires, the car is eventually going to rust out, just like the human genome.
And so I'm sad to say that's true, because I don't want to get rid of my cars, and I don't want to buy these new cars that are coming out.
But it's inevitable. Now. We're going to have to. So you could even grant, because we could be tempted as creationists. As you know, Sam, we've done a lot of open mics where an evolutionist will come in and they bring up what they argue is their best non-reductive beneficial mutation, like Dan loves lactose tolerance. Yes, there's the myelinase example in bacteria. There's a whole, there's really only a select few that they can point to. But rather than arguing all day about the hyper-specific details of what's going on genetically with those mutations, are they reductive? Are they non-reductive? You can just give it to them. And it doesn't help them in terms of genetic entropy.
Yeah, exactly. And in fact, in my simulation, I was extremely generous to them because in reality, there's something called antagonistic epistasis. Yeah. And that's where when you combine beneficial mutations, quote unquote, together, they work against each other instead of helping. instead of compounding on each other, you get less benefit the more of these quote unquote beneficial mutations that you get in combination. And that's called antagonistic epistasis. It's a real
there's
phenomenon.
too many beneficials going around that selection's confused. Like there's too much noise now. Is that what they're
No,
working
I think
against each other?
I mean, I think the fact that there is antagonistic epistasis is really strong evidence that these beneficial mutations are in fact reductive.
Oh, I see.
So
Okay.
I think it would be like if you had a boat that had an engine, and now you have a second engine, but the new propeller's facing the wrong way, and so now there's tension. Which way does it go?
something like that.
Yeah, two beneficial mutations trying to.
Yeah, they
confuse
work
each other.
against
Compete
each
with
other.
each other.
And I specifically turned that off. So in my simulation, I said, no, there's no antagonistic epistasis. Best case scenario for evolution. It's
Wow.
still crashed.
Amazing.
The population still crashed.
And you had mentioned in the debate, because somebody had a question, I think it was Jackson Rowe, how long, in light of slightly deleterious mutation accumulation, putting shelf lives on genomes, putting shelf lives on species in the biological world outside of humans, how long until extinction or inevitable population-wide genetic sickness? And you had pointed out, I think, as long as you're able to run your simulation, I can't remember what you said, 20, 30, 40,000 years, but it could even be shorter if you did not keep some of Zach's settings that could be wrong. Perhaps you can reiterate that, because I might not be getting it exactly right.
Yeah, so Zach's code, I told you already about the carrying capacity and how the settings cause an artificial dip in fitness if your population goes above the carrying capacity. Well, it turns out that his code actually has the inverse of that as well, which makes no sense. But basically it's saying if you're below carrying capacity, you get an artificial bump up on your fitness. And I failed to deactivate that in my code when I ran it. It makes no sense. Now, he tried to argue, oh, yeah, well, it's good if you got plenty of resources, so it should do that. Well, no, genetically speaking, not like having all the resources you need just means that there's nothing but pure genetics. Now, so it doesn't make sense to artificially bump up the fitness just because you happen to be under the carrying capacity. That's not a biologically realistic thing to do. But the whole point I made there is that, if I had deactivated that like I should have, probably it's possible that fitness could have declined even faster. I'm not sure. But the number of years that was, if you assume 20 years per human generation, then my estimate was 40,000 years for an upper limit. And it may be less than that.
Yeah, didn't Dr. Sanford say that it was a decrease at about 1.5 to 5% each generation?
He might have. I'm not sure. I'm not sure about that.
In the most simplest terms, is genetic entropy the reality that every generation, even with selection, is a little bit more mutant than the previous one?
Yes and no. This is a good opportunity to bring up the slides, because this is one thing that I learned from doing the simulation. It's a little bit slightly more nuanced than that. Essentially, Donnie, yes, but there's a caveat that I'm going to mention here. So, yes, 40,000 years. Okay.
Yeah.
Let me bring this up and view slideshow.
Now's a good time for this, Paul, so take your time.
All right. Are you guys seeing it?
Yes.
Yes, it says, why isn't the DFE balanced?
Why isn't the distribution of fitness effects balanced? Here's the reason. Now, back in the 1930s, there was this, well-known scientist Fisher, who came up with this geometric model. And he basically claimed, and this is something that Hancock has talked about as well and supports, but basically he's saying the reason why you get more deleterious than beneficial is it must be that your your population is far from a fitness optimum. It's far from this level of like perfection with respect to the environment. And so that's why. Well, that's silly. Is a pile of trash going to be easier to mutate than a Corvette? I don't think so. Just being far from a fitness optimum does not make it more likely that you're going to get more beneficial mutations. That is just silly. It's from the 30s, before the concept of DNA was even understood. The basis of heredity was not understood. The fact that life is based on information written in a code, none of that was understood when Fisher's geometric model was being developed. So, the fact that people in 2026 still think that we need to go on these primitive ideas from the 1930s is astonishing to me. But here's the real reason, and this is Dr. Philip Garish: even the simplest of living organisms are highly complex. Mutations, indiscriminate alterations of such complexity, are much more likely to be harmful than beneficial. That's why it's not balanced. That's why you get so many more deleterious mutations, because of functional complexity in the genome. So here's another way of putting it. Dr. Michael Lynch, one of, if not the most renowned population geneticists alive today. It's a lot easier to break a gene than make a gene. Yeah, isn't that the truth? Now, I believe this is known in the literature as Oda's ratchet, after Tomoko Oda. I just call it the fixation ratchet here. Under neutrality, the cumulative rate of fixation of neutral mutations is equal to the per generation mutation rate independent of the population size. Now, remember, the vast majority are going to be effectively neutral. So this is what Dr. Lynch is talking about when he says neutral. He's not talking about, strictly neutral with a zero selection coefficient. In fact, the leading experts don't believe such a thing even exists. All mutations have some effect. No mutations have a zero selection coefficient. So that's silly to even talk about that. But the cumulative rate of fixation is equal to the per generation mutation rate. Now, when he says cumulative, that means in the long run, when you look at it on the whole. So that doesn't mean that there's going to be fixations happening every generation. Far from it. In fact, it takes on average 4 times the effective population size number of generations before you're going to, on average, expect a fixation to happen. So in human beings, that would represent about 800,000 years. So on average, it would take us about 800,000 years to see one mutation fix in the population. So what does that tell you about how many fixed mutations we have? It's going to be very, very few. But what it does mean is on each generation, regardless of the population size, on average, you can set aside one individual's worth of new effectively neutral mutations as destined to fix. So it doesn't mean that they are fixed. It means that they're going to gradually increase in frequency over time. They're going to have this kind of random walk, this stochasticity, if you will. But in the long run, eventually they're going to go up and up to 100%. Now, that's what is represented there on the screen by the red double helix as opposed to the blue. These are all going to be deleterious mutations. But the blue ones are going to eventually just fall out of existence randomly through the random sampling effect, through genetic recombination. This is called genetic drift. So just randomly, all of those blue ones are going to be lost, but the red one is eventually going to be, if you give enough time, it's going to rise to 100% in frequency. But each generation, the number of reds goes up. You can't stop it. That's why it's a ratchet. So here's how it works in large multicellular eukaryotes.
Can I ask you a question about that?
Yeah.
So it seems like they would say, okay, well, you've got this population that is full of mutations that are coming into the population, not being fixed, but that would increase the probability of having them become fixed, and then potentially you could fix numerous mutations in a generation.
Well, it's all a law of probability, and it's very low probability for any mutation to be fixed, because you've got to start from one individual having it in the whole population, and you got to go from that to every individual having it homozygously in the population. So that's very unlikely. Only a small number is going to happen over. I mean, it's an ever increasing number, but it's a very small percentage. But it turns out that that small percentage is still enough to cause major fitness decline. So the first thing that happens is, one, growth happens exponentially until carrying capacity is reached or nearly reached. So, there's always a carrying capacity. An environment can only support so many of an organism. So while growth is happening exponentially to reach up to that carrying capacity, you're not going to have much entropy occurring, because it's too difficult for fixation to happen when the population is exponentially growing. But after the population stabilizes at a certain level, that's when things really start happening. Number two, the total segregating mutational load continues growing until mutation drift equilibrium is reached. Now, that's the point at which the number of mutations lost per generation roughly equals the same number that's being added. Now, why does that happen? It's because the number of mutations lost per generation is a function of the total number of segregating mutations. And so as that total number of segregating mutations increases, so too does the number that you're losing to genetic drift every generation. What that means is that there's going to be an equilibrium point where you basically reach a plateau, and the total segregating load of mutations doesn't keep increasing after that plateau. And that's something that I learned in the process of researching for this debate, because originally I used to think, I didn't understand that process, and I thought that the total load of mutations just kept growing and growing ad infinitum. But that's not the case, because you're going to get a point where there are so many mutations segregating that you're losing the same number of individual mutations every generation that you're actually adding. But number three, even though the total segregating load reaches a plateau, the percent of the load that is destined for eventual fixation is still growing each generation on average after the population stabilizes. So what that essentially means is that your average individual has a growing share of the total genetic load. And the ultimate result is that fitness declines linearly. And this is what I modeled. This is, you can see generation 0 up to like generation 7 or so, 6 or 7. You have this exponential growth. And then all of a sudden you reach carrying capacity, and what happens? Linear decline. Here's the segregating mutation load. You see exactly the dynamics that I was talking about. Exponential growth in segregating load, but then there is this plateau that it starts to reach, or to use the mathematical term, it starts to approach an asymptote. And if you look at the total segregating load in my sim, it looks like that asymptote is somewhere around what? Maybe 22,500,000 mutations, perhaps, is about where that line would be. That's your mutation drift equilibrium point. So after that point, you're essentially not, the total segregating load is not getting any bigger, because you keep losing as many mutations per generation as you're adding. However, here's that ratchet. Here's what causes genetic entropy. The mean deleterious allele frequency is telling us what percent of the load is en route to fixation. If you take the average individual in the population, what percent of that deleterious segregating load do they have as an individual? And as you can see, as the number of generations increases, this percentage goes up and up, which means that the average individual is getting more and more mutant because they're more and more likely to inherit a mutation over time. Does that make sense?
Absolutely.
This is it right here. This is genetic entropy.
There we go. Yeah, there's a lot of good points there. Even going back to the beginning of your slides with the effectively neutral mutation quote, that none would be strictly neutral. You'd mentioned in your debate that sometimes just in papers or if population geneticists are talking, I do the same, where we'll just say neutral, but critics might latch onto that and misunderstand that that's just somebody just quickly saying it. What they really mean is effectively neutral, that no mutation really has zero effects.
Yeah, and this is a problem even in the published peer-reviewed literature. This is a problem. Even in the scientific community, you get confusion about this, even among very high-ranking scientists. I mean, Dr. Felsenstein tried to argue strictly neutral mutations in the junk DNA. Mm-hmm. But scientists like Dr. R. Walker, Dr. Kitely, I believe Dr. Lynch, I'm not 100% sure what he thinks. I'm pretty sure he would agree. These scientists understand what Kimura put out, and Ota, I think, really is the one that is supposed to get the credit. Tomoko Ota came up with this understanding way back, but Kimura was the guy who published it in 1979. He had 0 strictly neutral mutations in his distribution. 0. Every mutation has some coefficient because every mutation does something to the genome. Even if it's very, very little, it does something. You can't change the genome without changing the organism.
To somebody who's new to this, they hear nearly neutral, strictly neutral, slightly deleterious, effectively neutral. Are these used interchangeably? Slightly deleterious, nearly neutral, and effectively neutral? Are there different definitions for them? Paul, how would you explain that to someone who's new to this?
There's a million terms for the same thing. Very slightly deleterious mutations are VSDMs. That's what Dr. Kondrashov called them. Dr. Kimura called them effectively neutral, and that's the same term that I think that's the most common term. It's the one that Dr. R. Walker uses, Dr. Kitely. So that's the term I would settle on because it's probably the most widely acknowledged term. But another term is near neutral. I'm trying to think of any others. Basically, all of these terms mean there is a very small selection coefficient, but it is drowned out by the effect of random drift. It is not going to be purified out of the population. Now, the other side of that coin is strictly neutral, and that is a fairy or a unicorn style of mutation that somehow has 0 effect of any kind.
Well, and it's so easy to refute the idea of junk DNA. They'll try and argue, Dan loves to argue, that the majority of the activity, biochemical activity, 80%, is just noise and spurious. We have great arguments for that. He likes to point to transcriptionally silent pseudogenes and ERVs. We have functions for those as well. So the point is, we could go down deep and show why the majority of the genome is functional, which means this problem, and this is an argument I've used in my own last several formal debates, that, hey, here's all the evidence against junk DNA. Here's the evidence for genetic entropy. The fact that you're not trying to counter me on junk DNA being overturned means genetic entropy really is an unsolvable problem, because then you have Dr. Felsenstein, is that his name? The population geneticist, trying to argue for junk DNA because he recognizes, if the majority of the genome really is functional, then there's nothing the evolutionists can do. But Paul, you pointed out that for sake of argument, if we're discussing genetic entropy, you can just grant them junk DNA, even though it's an indefensible position. And it still a problem they can't solve, even with junk DNA. I wonder what the max functionality, maybe you know the answer to this. What's the max functionality an evolutionist can hold to before it's too late? It's too much for genetic entropy. I wonder if it's 8%, 7%, 10%.
I'm not as up on the whole junk DNA debate as I am on genetic entropy, but it's a low percent. I think this is why there's a scientist named Dan Grauer who has basically said, if I'm only paraphrasing, but something along the lines of, if junk DNA is gone, then evolution is wrong, basically.
Yeah, false, he says. Yeah.
Yeah. So
they need junk DNA.
They cannot tolerate a highly functional genome because it makes it too obvious that the mutation load is a problem. But you can still grant them junk DNA. Here's the other thing. Even if there's a lot of junk DNA, just because it's quote unquote junk or non-functional does not mean that it would be a strictly neutral mutation, even if you grant that it's junk. Because even if it's junk, it's still it's junk that is in your genome, and your genome is highly interconnected with itself. There's 3D folding. I'm sure you guys are aware of this. You know, the 3D folding that happens with DNA and all these interconnected points, where points in the code that are, if you line it out linearly, they're far apart from one another, but they actually touch in the 3D folding and they affect one another. So even if there's a lot of so-called junk in there, that doesn't mean that you can mutate that junk without having any effect on the organism. It still doesn't mean it's going to be a strictly neutral mutation, even then. So their problem is worse than that, because even with junk DNA, the mutations that occur in the junk are not going to be strictly neutral. The experts acknowledge this. And you can go a step further. You can grant them, unrealistically, you can grant them, okay, all of the mutations that do fall in the junk will be strictly neutral. You still have genetic entropy because the mutations that hit the functional part are still going to cause fitness decline. There's still no mechanism to prevent that.
Well, it's an incredible. I do have something to say, but Sam, I want to hand it to you if you had a question first, brother.
No, I wanted to just reiterate those two quotes that you said. It's easier to break a gene than to make a gene. Yeah. And the one about slightly changing a complex system, Michael Behe made that argument in his book, Darwin's Black Box. And he used the analogy of something like a Rube Goldberg machine, where you got this very complicated machine, and it's not going to take much to mess that up. And it kind of made me think during the COVID year on the internet, people were doing some amazing things by bouncing a ping pong down multiple stairs and have it bounce off cups. I don't know if you guys have ever seen one of those. And one slight move in one of the plates or the cups, that's just going to upset the whole trajectory of the ball there. And so yeah, similarly, if you have a deleterious or harmful mutation in a very complex system, you're more likely to have a catastrophic type of problem.
Yeah, and think about it like this. So like the Rube Goldberg machine, like you're talking about. Now imagine that you have a whole bunch of trash laying right next to your Rube Goldberg machine, okay? And we're gonna use this as an analogy of junk DNA. And we're just suggesting, okay, for the sake of argument, you've only got a small percentage of the genome that's functional and the rest is trash. Okay, so now you've got your Rube Goldberg machine here and trash all around it. And then you start randomly moving that trash. What if some of that trash falls into your Rube Goldberg machine?
Yeah.
The point is, even if you grant junk, randomly mutating that junk is connected to your functional genome. So it's still going to have an effect, even if it is junk.
Yeah, I think it's a bold statement to just say that there's this much junk anyway.
It is.
How would they even know that?
Well, it's an argument from ignorance.
Yeah.
We don't know the function, so there isn't one. And
well, it has to be junk on their paradigm.
What's that?
It has to be junk on their paradigm.
It has to be, exactly.
To be.
And that's their assumption, because they believe that random mutations are the building blocks that created life from scratch. They're denying that life was designed intelligently from the start. And so, of course, they think that there's going to be a lot of junk. And, I don't think that there's very much junk, but I don't think as a creationist we have to disavow all junk either, because it's possible over the thousands of years since the fall that some non-functional code has crept in through mutations since the fall. I'm not saying it would be much. However, we don't have to say that the genome is 100% functional, because it's possible that the effects of the fall have created some non-functional code in there. I'm
Right.
not discounting that possibility, but I don't think it would be very much, because we've only had, 6,000 years of history. There's not enough time for almost anything to have been fixed. As I said, fixations happen much too slowly. So our genome is not that far from what God created. It's just that it's enough damaged that we're starting to see problems. We do have, the human race has a lot of genetic problems, in case you didn't realize. I mean, the number of birth defects and genetic diseases is very high. And without modern technology, our lifespan would probably be in the average range of about 40 years, just like it was historically. We haven't gotten healthier since the time of the Romans. We've gotten less healthy since the time of the Romans. Genetically speaking, we might have better nutrition in some cases on average because of the greater amount of wealth. And we certainly have higher technology, which enables us to overcome a lot of these problems that they didn't used to be able to overcome. But no, we have, think about it this way. In the Bible, David wrote in the Bible an average, or if you're doing well, you can live 70 or maybe even 80 years, right? That's in the Bible, in, I believe, the writings of David. And don't ask me where, because I can't remember. Maybe in one of the Psalms. Maybe you guys know. But think about him writing that all those, hundreds and hundreds of years ago, when they didn't have technology to keep people alive that long.
Right.
So that means that we've actually degraded since David's time, because without modern technology, I guarantee our average lifespan would not be 70 to 80 years. We would be dying out a lot sooner without medicine and hospitals and doctors' offices. So we've declined further since David's time.
Intelligent intervention. That's what it would be.
Exactly.
And I think it's really interesting. Raw Matt, one of the guys on the team, he did a debate, I think a few years ago now, about longevity and defending the long biblical ages. And at the time, the critics, they wanted to argue against that. But now there are many secular scientists coming out acknowledging that, yeah, if they can correct some of these mutated genes that are related to the quality of life, that intelligent intervention again, then you can correct the genome to live, much longer lives, better quality of lives. They're talking about reverse aging.
And here's one of the really cool things that I have only relatively recently come to realize. The pre-flood world, there was something very different genetically, and I don't think it was limited to just humans. I think it was probably all large multicellular eukaryotes like humans. But there was something different about the total life stages. So, it looks like as our longevity decreased, the time to reach sexual maturity also decreased as a proportion of our lifespan. So we reach the age to reproduce now at mid to upper teen years. But if you look in the pre-flood world, they weren't having their firstborn until they reached sometimes in the neighborhood of 100 years old. And what that tells us very likely is that they were living as children or teenage or preteens for longer than most of us live our whole lives now.
Oh, that'd be horrible.
That'd
Can you imagine the terrible twos for a whole decade?
be tough.
Exactly.
You talked about double speak from the secular camp, and so there, that's a perfect example how on one hand, they have to say that something like genetic entropy isn't a thing, but on the other hand, I think the most prominent field of study right now within the secular camp is in the field of longevity and correcting what has been damaged biologically. So you can't have it both ways, guys.
Oh, no, you can't.
And in your presentation there, Paul, you touched on something significant, and perhaps you can speak to it in a little more detail just to show the audience why it's so important. But this comes back to the effectively neutral mutation point. Even with junk DNA, it'd be very difficult to argue for a strictly neutral mutation that has zero effect on fitness. But this idea that, and you quoted a population geneticist in your presentation, but Fatuma, famous evolutionary scientist, he also stated the same thing, that the per generation or the neutral mutation rate approximates or equals the fixation rate over time. And a big thing that evolutionists forget is that although fixation is zero today, basically, if you get a random mutation somewhere in Australia in an individual, it's almost a 0% chance that's going to spread at that site to every person on the planet. But in the evolutionary model, Paul, they actually, if you had a pen, the last 6,000 years is just the tip of that pen in evolutionary history. The majority of their history, they have human beings existing in smaller, isolated populations, existing in tribes in Africa. Therefore, you'd have faster rates of fixation, a lot faster than today. And so there's a counterbalance where, today fixation is basically zero, but for most of evolutionary history, fixation would have been a lot faster. Therefore, over longer periods of time, the neutral mutation rate approximates the fixation rate, which means every time you get one of these slightly deleterious mutations fixed in place, that's damage population-wide, that unless you get a rare back mutation, that's now established in the population. Selection can't do anything about it.
Yeah. Yeah, I mean, this is exactly why Kondrashov wrote, "Why haven't we died 100 times over?" Because he understood that on an evolutionary timescale, this doesn't make sense. We should have already gone out many, many times over by how quickly genetic entropy actually happens. It doesn't fit with their timescales at all. And that's why I think it's legitimate for us to call this an independent line of evidence against radiometric dating methods and for a young Earth.
Well, I like to say genes, traits, and genetics. That's what's inherited sperm and egg. That's the direct way to answer this question of ancestry. Not a bone, not a rock, not a fossil. These are not direct, or as Sam likes to say, high confidence versus low confidence science. We can actually see these mutations every generation. We can see that they're pouring in to pop. I rewatched Dr. John Sanford's NIH lecture just the other day. Such a great lecture. Watched it many times. And he talks about 7 to 8 billion people on the planet, 100 new mutations per person per generation. That's 700 billion new deleterious mutations just this generation alone. So undoubtedly putting shelf lives on genomes. And then, and maybe you can speak to this, because, how do we extrapolate this to the rest of the biological world? In the Q&A at his NIH lecture, somebody asked, well, what about organisms like horseshoe crabs that you would find in hundreds of years worth of rock strata? How are those still around if we're supposedly degenerating? And Dr. Sanford pointed out that, okay, here's the philosophical issue. Yeah, if mutations put shelf lives on genomes, well, that would mean that species cannot persist for millions of years into the future. Neither could they have persisted for millions of years into the past. So if you see a horseshoe crab in 300 million years worth of strata and relatively the same kind of horseshoe crab today, what we know about slightly deleterious mutation accumulation means that that horseshoe crab, as a fossil, which is extinct biology found in that rock strata, shows that that rock strata cannot be millions of years old. Because
Cannot
that
be.
horseshoe crab could not have existed for that amount of time. Obviously, population.
And also the problem of genetic entropy also refutes the concept of evolutionary stasis, because we know that no environment is able to maintain stasis over time because of the problem of effectively neutral mutations. You can't maintain stasis. The typical explanation for stasis is what, guys? It's, well, it didn't change because it was perfectly suited to the environment, right?
It didn't have to change. The environment was good.
The environment was good. Well, what about effectively neutral mutations? They don't care about the environment. Why didn't effectively neutral mutations cause a change over time, even if it was perfectly suited for the environment? That explanation doesn't cut it. There should be no stasis. Never. Because there's no way to maintain that stasis. Here's an interesting article. I'm putting it in the chat. This is one of the things that the skeptics will constantly say, well, we don't observe genetic entropy. It's never happened. Why doesn't it happen? Well, here's an example where even the evolutionists admit that it happened. The woolly mammoth died because of genetic entropy. And that's what this article states. They don't use the term genetic entropy. But guess what they're saying? The last woolly mammoths went extinct because why? They were in a small, isolated population and they had genetic meltdown, mutational meltdown. Well, guys, what is that? That's genetic entropy.
Genetic degeneration. And they'll say, oh, well, these mammoths, or I like to point to the Neanderthals or Hobbit. With Neanderthals, we actually have their DNA to show that they were highly inbred. They were 40% less fit. Mammoths here, this is a great article where they faced genomic meltdown. They were, a lot of the recessive mutations came to the forefront. They were isolated, led to rapid and accelerated genetic degeneration. But isn't that like a small scale example? We have this isolated population where all these deleterious mutations that have been accumulating, a lot of them are in recessive form. Inbreeding reveals the hidden reservoir of genetic mistakes that have been accumulating. So those species go downhill. A lot of them go extinct, like with this case with the mammoth. If we were to extrapolate that population wide, right? Humans, we're not just isolated on some island. I mean, we exist globally. So that's a small scale example of what genetic entropy could do. Is that right, Paul?
Yeah, exactly. The smaller the population, the faster it happens. So, small isolated populations are always at great risk for very fast genetic decline. But, the whole Earth is what? One big isolation chamber, right?
That's a good point.
The planet, we're isolated on this planet. There's no better beings, unless you want to count Genesis 6, where things are happening from outside this planet. So this whole planet is one big isolated group of genetically isolated population. The same process that caused the woolly mammoths to die out is happening to all of us, just at a much slower rate.
So I put a link in the chat as well, and it's a link that I think would be a problem for anyone that outright denies that genetic entropy is taking place. And it's an alphabetized list of, I think, thousands and thousands of genetically inheritable diseases. So how did those get, what's going on there on that paradigm? Are they coming? Are they going? What are they doing there? And there's thousands of them. So
I think it's just kind of evidence of genetic decay. What is a disease? It's when something isn't happening the way it should. So, the fact that we have this many is, if you were questioning whether we're in decline or how far along we are, yeah, this is what I'm talking about. We have a lot of genetic problems, and the only reason that we're able to do as well as we are doing is because of modern technology. Right. If we lost our modern technology, I'm sorry to say, natural selection would suddenly come into effect much more strongly.
Mhm.
And that doesn't mean that genetic decline would stop, by the way, but it does mean that a lot of people would die and our average lifespan would go way down and infant mortality would go way up.
Yeah, because critics like to argue when we show them the clear evidence for genetic decay in the human genome and human population, they'll say, well, we're experiencing relaxed selection because we take care of each other, we help each other out, medical advancement, medicine, so on and so forth.
And what's
we don't
the
have that in the
implication of
wild.
that? The implication of that is they're saying we should stop helping people because we're hurting our genes.
Right. Yeah.
Yeah. Eugenics. But still nothing would follow from that. Just, I mean, yeah, we are experiencing probably a relaxed form of selection. People are on medicines and things like that. But the bigger question that just kind of ignores the whole argument is that those are there for a reason.
Right.
They came into existence and they weren't there at a time in the past.
Why do we need all those medicines? Why can't we just live healthy?
Yeah.
Mm-hmm.
I mean, those pharmaceuticals didn't exist when we were living, around the time of the creation or shortly after the flood, when we would have been living in more primitive conditions. And so, yeah, I mean, that's my point there with those genetically inheritable diseases. They're serious.
Right.
They have to explain how those all came about at a time when even on their model, they have to acknowledge that, be it give them 10,000 years ago, we didn't have any of these modern technologies or medicines and things like that. So many of these could not have existed.
Yeah. And like somebody in the chat, I think Nick Dev is mentioning people on like jungle, like uncontacted native tribes and people like that in small islands. And like, there's one example where there's a group like that off the coast of India. And I think the government of India has outlawed anyone going to the island thinking that they're helping these people, right? I'm sorry, far from it. If you don't get those people off that island, they're going to die a very unpleasant genetic death from inbreeding. Inbreeding is terrible. Why would you consider that to be good? Why would you say, okay, we know that there's this small tribe of people that are out there inbreeding, endlessly inbreeding, and we're not going to lift a finger to help them. We're not going to, I mean, I would say it's inhumane that they're allowing it to continue like that.
Well, the fact that they even invoke the argument, well, we'll relax selection, so we're not degenerating as quickly. The fact they're even saying relax selection, pointing out modern medicine and us helping each other. Yeah, okay, if you were to take that stuff away, then we would degenerate more quickly because now we don't have various medicines and help certain people in the hospital. So that is acknowledging there is a problem, in the same way that all of these papers we like to cite, we see certain mechanisms or rescue devices invoked, like synergistic epistasis. I mean, I've debated evolutionists who are like, oh, genetic entropy is not a real thing. It's just made up. Here, look, here's a paper on synergistic epistasis, how that solves the problem. You just said genetic entropy isn't a problem, but hey, here's a so-called solution to a problem that doesn't exist.
I tested that theory. I did test that theory.
Is that synergistic epistasis?
Yeah, I ran my simulation with different levels of synergistic epistasis. And the more synergistic epistasis you put in, the faster the fitness declined.
Wow.
Because what it does is that it just makes the problem worse.
How come?
Because synergistic epistasis means that you're causing the deleterious effect to be more than multiplicative. So in the standard model with no epistasis, let's say that you have, a deleterious mutation with a selection coefficient of, minus 0.02. And let's say there's another mutation with the same one. So another minus 0.02. Well, in the standard model, you just multiply those two together and to get your new deleterious coefficient, multiplicative model. With synergistic epistasis, it's increased above that. It's more than multiplicative. So it's even more deleterious in combination. And their hope was, well, if we can make it deleterious enough, then maybe we can push it past the drift barrier and it will be selectable, right? The problem is that mutations happen homogenously across the population. So you don't get much fitness variation between individuals because the mutation rate is basically homogeneous. So when you introduce the epistasis there, you're just making fitness decline faster. You're not enabling purifying selection because everybody's mutating at roughly the same rate.
So what if they say, well, mutations accumulate effectively neutral, selection doesn't see them, but then eventually they build up enough in a population where now Mother Nature can see that this group within the greater group now has more mutations, and therefore selection can deal with that and then solve the problem or slow. I mean, at the end of the day, okay, you want to slow down the degeneration that is inevitably going to degenerate. So have you heard that mutation count mechanism or this idea that eventually it builds up? So how would you respond
it just
to that?
doesn't work because mutations happen homogenously. So you don't get, unless you have geographic isolation with smaller population sizes, you don't get much of a fitness gradient across the population.
I see what you're saying.
But if you do get that fitness gradient, it can happen. Like, some groups of people are known for having really bad teeth, and those people may or may not be small isolated island livers, people who lived on an island in an isolated population. So I'm not saying that there's no fitness gradient at all, but even if you look at this, so let's say you have a smaller population over here and a larger subpopulation over here.
Yeah.
What we expect to see is the smaller subpopulation is going to degrade faster. That doesn't mean that the larger subpopulation doesn't degrade.
Right.
They also degrade, just more slowly.
Yeah.
Everybody degrades.
So in a way,
the smaller your population, the faster that degradation happens.
Right. So it does nothing to solve the overall population-wide degeneration since, and we've discussed this before, every single individual, everybody's multiply mutant. We all have a complex combination of nearly neutral, slightly deleterious mutations. And so I've seen Rob Carter use the analogy, I think it was in Evolution's Achilles Heel, where he said, take a room full of 100 people, everybody has mutations. Everybody's more or less more mutant than the previous generation, than their grandparents. And so if you were to just have strong selection, remove 50% of the worst mutants, so now you're left with 50 people, or you're still left with 50 people that are more mutant than the previous generation. And I know it's more complex than that, Paul, in light of your slides earlier when you were talking about the fixation. And actually, perhaps you can expand on that a little bit. So you were saying earlier in your slides that the mutations build up so much to the point where there's like mutation saturation. And so a lot of mutations are kind of being balanced out, where they're being weeded out, but then you still have mutations coming in. So it's keeping it at this nice balance. Or I was trying to fully grasp what you were saying there. Can you reiterate some of that?
Okay. So what you're referring to is the mutation drift equilibrium.
Yeah.
And what basically drift is how there's a randomness to what happens to any given mutation over time. And that randomness has to do with the genetic recombination, right? So when recombination happens, it's like shuffling up the alleles, and you may or may not get that mutation, right? So the formula for, so basically what that means is that each generation, there are mutations that are going to be lost. They're not being weeded out. That wouldn't be the right word. They're not being lost because of any selection happening. They're being lost randomly due to sampling, genetic gametic sampling.
Okay.
It's just, it happened to get unlucky, or luck, however you want to look at it, lucky or unlucky. That mutation happened to not get passed on just through random sampling.
So it's not that selection is acting in the way the evolutionists want. It's just random sampling.
It's random sampling. It's not selection at all. It's genetic drift, which is random gametic sampling.
Mm-hmm.
And the more mutations that you have, the more opportunities there are to lose a mutation.
Right.
And so that means the more you have, the more you lose every generation.
Yeah.
But you have this constant in stream. So it's kind of like if you have a hose and you dig a hole and you start pouring water into the hole. What's going to happen? The hole is going to fill up with water up until it reaches the top, and then what? Then any
Spill.
excess just spills over.
Yeah.
That's kind of what
That's a good
happens with the
analogy.
mutation segregating load. You fill up to the full load that the population can support, and after that, you start spilling over through random loss through genetic drift. So the total amount of the genetic load does, theoretically at least, reach an equilibrium point. And that's like when the water fills up the hole and starts spilling out. However, the ratchet still happens. The fixation ratchet is still in play there. So what that means then, like I said, even though the total load, the term is segregating load, even though that segregating load stays relatively constant after that point, you have mutations that are part of that load that are gradually increasing in frequency, and that percentage grows each generation. That's the fixation ratchet. So even though the total number of mutations isn't growing after a certain point, over time you have a higher and higher likelihood that you're going to inherit one of those segregating mutations or multiple of them.
And with that also, because you have all these mutations pouring in generation after generation, most of them are lost, but many of them are not. So when it goes back to this neutral mutation rate approximates the fixation rate, yeah, most are lost, but there's just so many entering the population. Kind of like if we had a highway and you just had 1,000 cars entering the highway, you'd have many, maybe they get off at an exit or they stop at a gas station, or a lot of them get off the highway, but you have so many cars that are going on the highway that you're still going to have at least a few that make it to the end, aka fixation. And so you still have mutations fixing, which is a problem again, as we pointed out earlier, because now that's damage established population wide.
I mean, think of it like if you're going to use the highway analogy, imagine you have the blue cars and the red cars. The blue cars are cars that are on the highway that are eventually going to exit.
Mm-hmm.
The red cars are on the highway and they're never going to exit. They're going to stay on the highway. And every time you go 5 exits, a new red car enters the highway. So even though, and one blue car enters at the same time, leaves at the same time. So the total number of cars on the highway isn't changing.
Right.
But every 5 exits, one blue car is replaced by one red car. What is that going to mean? Over time, the number of red cars is going up, even though the total number of cars on the highway isn't changing.
Wow. It's exactly why this paradox has not been solved. I mean, this really is a problem that I would argue precludes, as in makes common descent impossible, but it also acts as an evidence that contradicts dating methods as well, because you have genetic entropy puts shelf lives on biology, but we also have extinct biology all throughout the so-called geologic column, going back supposedly 500 million years ago plus. But all those billions and billions of fossils that we find were once living biological organisms. So that means there's a shelf life on those fossils, those extinct organisms, and therefore they're found in rock strata. So that also puts a shelf life on the rock strata itself. So in a way, it's a genetics related, biology related argument, but it both acts to refute common descent and an old earth.
Yep. And the best you're going to get from, and this is what typically happens and this did happen in the Peaceful Science Forum, once you have nailed them down on point after point and they've got nowhere else to run, they're going to say, well, there must be some problem with the theory, even though we don't know what it is, because we know evolution is true.
Yeah,
so there's some problem with the theory, even though we can't tell you what it is.
It goes back
where
to
they are now in that forum.
That's all they
That's where they are now. And in fact, he's saying it's like proving that bumblebees can't fly.
So yeah, which begs the question, but where's Dan been in all of this? I mean,
he's been absent.
Absent?
Both he and Hancock have been completely absent, and they have washed their hands of it, which is very surprising. You can see neither one of them are here tonight, and normally Dan would be all over this.
And for the record, because we're almost at 2 hours, I've been posting this link, and we've had this scheduled for a while, for serious evolutionists, those that believe they're related to banana plants and grass, who want to prove us wrong on genetic entropy. So we've been willing to engage the critics on this issue. And it not only goes for genetic entropy, but they're failing in related topics too, because in the same way that we're talking about these effectively neutral mutations, Paul, you can look at all these, and Sam and I've been talking with Matt, we're preparing for a debate coming up on this issue. So it's kind of fresh on my mind as well. These pedigree studies that we love to look at, Paul, on the mitochondrial chromosome, like Parsons and Santos and Howell, that give a fast substitution rate, a lot faster than evolutionists ever predicted. Parsons pointed out that if we were to just extrapolate backwards, we get 6,500 years. They hate that. And so Dan and the evolutionists, they appeal to purifying selection. Selection saves the day, just like with combined with beneficials for genetic entropy. But no, these studies are looking at the D loop or control region, which is largely neutral. So sure, you can have some selection outside of that in the coding regions of the mitochondrial DNA, but those studies are not even looking at that. They're looking at the D loop region. Those mutations accumulate in a neutral fashion. Neutral mutation rate approximates or equals fixation rate. So even with selection, it's a problem for them. We still get that roughly 6,000 years. And so the point is, on mutation rates, genetic entropy, I mean, we can name a whole bunch of other things. It's a great time to be a biblical creationist. They're on the defense. We're willing to engage them on it. We're willing to have an open mic here.
I would say when it comes to genetic entropy, they're not even on the defense anymore. They're in full retreat.
I like that. Yeah, they've gone from offense to defense to full retreat.
Full retreat. Their backs are to us. They are running off the battlefield.
Well, they had fun for a minute when the paper came out.
I don't even think they had that much fun, because every time one of their cheerleaders would bring up the paper in a debate or open mic anyways, I'd say, okay, reiterate what the paper is saying. How does it debunk genetic entropy? Well, I don't know. They don't even really understand the paper. So they're still easy to refute. So I want to ask you this then, Paul, because this might be a good clip for the creationist community, because I'm going to share this around everywhere. Genetic entropy in 2026. Critics still haven't solved us, prove us wrong. We haven't been proven wrong. So here's my question. When confronted, either in a discussion, in person, Facebook, a debate, somebody throws the Hancock Stern Cardinal paper at them and says, genetic entropy has already been dealt with. How, in a nutshell, elevator pitch response, perhaps, and we could also put a clip out like this to pass around to people, what is the best way to respond to that assertion that, hey, this paper right here, this has overturned genetic entropy?
I would just quote Dr. Zach Hancock, who's the lead author of the paper. I would just quote him. He says, if genetic entropy equals Kondrashov's paradox, as Paul plainly states, then these simulations are irrelevant.
Wow.
I would just quote him, because he's admitted that his simulation does not overturn Kondrashov's paradox. And Kondrashov's paradox is genetic entropy in large part. If you read Dr. Sanford's book, you'll understand that, which he should have understood that, because he claimed to have read the book already. So the claim that he's making, he's implicitly acting like he didn't know that when he says, like, as Paul states, it's kind of implicitly, oh, well, I didn't know genetic entropy was Kondrashov's paradox. Well, why not? You've made video after video. You claim to have read the book. You should have seen it in there. But anyway, just quote him. It's irrelevant. His simulation is irrelevant because it's not addressing the problem.
That's flabbergasting to me. I mean, Kondrashov's paradox, correct me if I'm wrong, is the concept in biology that genomes should be degenerating due to a fast mutation rate. Those mutations are largely harmful and deleterious, and they build up.
Yeah.
Isn't that genetic entropy?
Yeah, it is.
How is that not? So how would they try and counter that to try and say, no, they're two different things?
I think the debate over that paper is over, to be honest.
Yeah.
That paper is a has-been thing now.
So has that paper overturned anything then?
Nothing. I mean, not that I'm aware of. The paper was about two different topics at once. It was about genetic entropy in general, but it was also about the
Fisher's theorem.
The Fisher's theorem part.
Yeah.
And so I'm not even going to touch that because I'm not too familiar with all of that derivation and math on Fisher's theorem. I'm not even going to touch that part of it. But when it comes to the genetic entropy part where they did the simulation, that part is, as Hancock states, irrelevant. It does not solve the problem.
Yeah, but Paul, if genetic entropy were true, mice and bacteria should be extinct by now.
Not so. Put the parameters in.
Let's just throw that in there.
Yeah, it's not the case. That's one of the claims Dan Stern Cardinal has made. I've challenged him to put his money where his mouth is, and he's refused. But if you think mice are a problem, then do your research, use my code, and put the correct parameters for mice into my simulation and see what happens. See how long it takes mice to go extinct if you use the correct parameters. Mice have a much larger effective population size than humans. What does that mean? More effective selection.
Right.
They also have a lower per generation mutation rate. So there's less mutations happening per generation, and they have much larger population sizes. These two things together make genetic entropy much weaker for mice than it would be for us. So if you think mice should be extinct, put your money where your mouth is. Do the simulation. Nobody's done that.
So we can confidently, so an evolutionist, let's say Sam and I were preparing for another debate on Adam and Eve, genetic entropy, great supporting argument for that on top of others. If they cite synergistic epistasis, if they cite Dan and Zach's paper, we can show them your simulation, your work. You talked about earlier how you ran the synergistic epistasis rescue mechanism. It doesn't work. Your simulations are real hard data showing that these rescue devices fail.
You put the math in, you use the correct parameters, these rescuing devices all fail. And they know it fails. I think Zach Hancock knows that it fails, and that's why he chose to change the subject and start appealing to a totally different paper, which was Charlesworth, where he totally redefines the problem and obfuscates the problem and doesn't solve it, but he totally changes the subject. In fact, if you look at Zach Hancock's channel, his last upload is titled, "Do Genes Even Matter?" So he's like going into this la-la land now of like genes, they don't even matter. It's all about traits.
So he's getting desperate.
Yeah. Oh yeah. Big time.
Wow. And another thing you guys kind of talked about in the debate as well, and is the fact that selection's acting on phenotype, not genotype. So all these different mutations that have accumulated, it's not, a lot of people get confused. They think, oh, selection's going in and looking at all these nucleotides. Oh, this one's good, this one's good, oh, this one's bad, so let's remove. No, I mean, it's either the entire organism, selection on the entire organism, or none at all.
Exactly. It's organism wide. It's not, it's not the selfish gene like Richard Dawkins ignorantly claimed. Genes are not selected. It's individuals. And the latest science is decidedly anti-selectionist. Dr. Michael Lynch is probably one of the best guys to go to understand where the cutting edge of evolutionary population genetics is right now. And you'll never believe where it is because it's nowhere near Zach Hancock, or definitely nowhere near Daniel Stern Cardinal. Here's the cutting edge of population genetics now. Basically, they've thrown selection out because they know selection doesn't work. Selection cannot be the mechanism. So guess what Michael Lynch is saying? He's saying evolution must happen during periods of very small population sizes when drift can fix lots of stuff really quickly. And it's going to be deleterious, yes. But he's banking on what apparently there's this term I learned recently called sign epistasis. SIGN epistasis. Sign like you're changing the sign of an equation, like plus to minus, minus to plus.
Mm-hmm.
Sign epistasis is what they're banking on now. They're saying, okay, lots of deleterious mutations are going to accumulate, but then they're going to connect together functionally, even though they're deleterious, but they're going to connect functionally, and you're going to have sign epistasis. And suddenly what used to be deleterious now becomes highly functional, complex, beneficial, additive information. And that's what they're banking on. That's what Michael Lynch believes. He believes evolution happens during periods of small population where lots of mutations can fix rapidly. And by some miraculous chance, you get deleterious mutations combining to form complexity and beneficial results. Sign epistasis.
So you'd have to have just an unimaginable amount of bottlenecks in every population of every organism, right?
Oh, yeah.
Change.
And then somehow, miraculously, the population cannot go extinct through that bottleneck. It has to persist, and this miraculous rescue has to happen somehow. Somehow, without selection to guide it, you have to build functional complexity through deleterious mutations.
But then they would have to point to something, like something within the geological column. Like they're going to have to justify that somehow. Where's the evidence of these?
Well, they're going to line stuff up. Look, this creature evolved into this creature because this creature is primitive. It's lower than this one.
Sam, here's their justification. We're alive, aren't we? We're here, aren't we?
It had to happen. And
we're not dead. It must have happened.
Yeah.
That is actually another thing that Zach Hancock said in one of his videos, where he said, look, it can't be a real paradox. Otherwise, we wouldn't be here.
Yeah. Well, maybe it'll be aliens here soon, you know?
So basically the answer to the question, why are we not dead or extinct 100 times over? Well, I mean, we're here. So, I mean, that explains it.
The cutting edge of evolutionary science, the answer is, we don't know, but we're here, aren't we?
Yeah.
It happens somehow.
They don't. Yeah. There's just problem after problem that it's these gaps. I mean, it was just like in a debate we did the other day on Modern Day Debate, we were pressing them on the mutually interdependent systems. What came first? DNA repair enzymes, and there's several other we could. Well, the answer is we don't know. We don't have an answer right now, but that doesn't mean, and then Sam pointed out naturalism of the gaps, right? No, these are major issues that if they don't have answers to, like Paul, the genetic entropy issue, well, their theory, it's not even it's off the table. What's on the table? Well, exactly what the Bible describes: a special creation, separate ancestry. We've only been here for 6,000 years. We've only been accumulating mutations. So it's not an issue for us, Paul, because we've only been accumulating mutations for 4,500 years. But if you want to stretch that back millions of years, now it's a problem, right?
Yeah, exactly. And, you know, I know this quote always gets mentioned, but there's a good reason why this quote always gets mentioned, because it's so true of what's going on. And that's the Richard Lewontin quote, who was a famous geneticist. You know, his quote, and here it is right here. I'll put it in the chat. All creationists should have this quote basically memorized, because it's so important to understand what they're doing.
What's the quote? Can we read it out? I'll pull it up right now too.
It is, well, I'm not going to read the whole thing, but
Oh,
Part
okay.
of it says, it's not that the methods and institutions of science somehow compel us to accept a material explanation of the phenomenal world, but on the contrary, that we are forced by our a priori adherence to material causes to create an apparatus of investigation and a set of concepts that produce material explanations, no matter how counterintuitive, no matter how mystifying to the uninitiated. Moreover, that materialism is absolute, for we cannot allow a divine foot in the door.
Yeah.
And that's the final answer. That's what's happening. And you win the debates with them, but they're never going to admit anything because they cannot allow a divine foot in the door.
Right.
This is what happened when I debated Mark
Reed.
Mark Reed. Yeah, that's how the debate went. He kept backing up to, I don't know. I don't want to talk about abiogenesis. I don't know. I don't know. But you can't say God did it. Why? Because that's not scientific, they say. Only because they've hijacked the definition of science. Obviously, science didn't start out that way. But at some point in the late 1800s, it got fully hijacked by these guys.
Yeah, I mean, it's a philosophical position to say that, like a physicalist or a naturalist, and so it's useful to some degree when you're interacting with the physical world, perhaps, but at a broader worldview level, that philosophy just doesn't stand on its own. So
No.
when you go outside of but even the foundations of science, in our debate we pressed Ron Garrett pretty quick on what provides for the uniformity of nature. That's an assumption that needs to be justified. But on naturalism, what would that be?
Nothing.
There's nothing there. So, that's where we talk about them borrowing from our Christian worldview.
Yep.
And that's why it was Christians that began the scientific method. It's our worldview that would justify the exploration of the world, and that the conditions that we experience today are the key to understanding the past, as long as it's on a biblical timeline. And we know this because God has a plan and a purpose for his creatures, which would be us, and he's going to use creation to do it. And he talks about things that have not yet come to pass. And because of that, we can justify the uniformity of nature. And so, yeah, they've got more than just scientific problems. They've got a worldview that's in shambles as well.
Exactly.
Well, we've essentially, because I've tried to throw just everything at you, Paul. In my years and years of doing this and engaging critics, mice, bacteria, mutation count mechanisms, synergistic epistasis, super beneficial mutations, Dan and Zach's paper there. I love that you taught me a few things today, but in Dr. Sanford's book here, I think you said page 116, he directly refutes that.
Yeah.
To confirm, is that the infinitesimal model that Zach relied entirely on the infinitesimal model in his opening statement, yet that's debunked here.
Yes.
Didn't try, and they haven't tried to defend their paper. You've already overturned that with your simulation.
Yeah.
What do they got left?
The infinitesimal model is basically a rejection of the whole foundation of population genetics, and it's saying, never mind, mutations don't have effects individually. Instead, it's all about these traits. But what is a trait? A trait is a subjective thing that we decide as a human that we're interested in. Yeah. So that's why he talked about agriculture and corn oil and stuff, because if you subjectively decide there's something you're interested in, you can define that trait and you can selectively breed for that trait. But genetic entropy has never been about traits. It's about mutation load. It's about individual mutations with deleterious effects that are causing harm to the genetic code, building up, and there's no mechanism to purify those. That's genetic entropy. So Charlesworth's paper and the infinitesimal model completely sidesteps and avoids the whole issue and just tries to change the subject.
These traits, finch beak size and what he was talking about in agriculture, because he said, oh well, maybe you guys don't like the corn or the agriculture. Well, here's some adaptive episodes in finches.
Does he not know that John Sanford was deeply involved in that whole world of plant agriculture? And
he's a plant geneticist.
Yeah, he's the plant geneticist.
So how do we know these traits are these came about due to mutations or alleles associated with I would ask the question, how do you know this isn't design diversity? I mean, if I see these adaptations taking place and these traits manifesting, and how do we know these aren't designed alleles or design traits? I mean, there's so many questions, I think, and assumptions in that model too.
Yeah.
That I would
and one of the things, what I would suggest, if you want to go really deeper into this, Donnie, I would suggest you actually watch Dr. Michael Lynch's Intro to Population Genetics. It's eye-opening. And yes, it's a little technical. It's even over my head a lot of the time, but I still gained a lot from it. And I would recommend that you watch both parts of his Intro to Population Genetics. And if you do that, you're going to have a leg up on almost every PhD scientist in the world. I promise you that.
Is that
in any debate?
Is that lecture 1 and lecture 2? So it's a 2-part? Or
it's a 2-part, yeah. And I cited it in my debate. Let me see if I find it.
I think I see it here. International Center for Theoretical Sciences.
And it's, hold on.
Yeah, Wesley Coleman's interested as well. That's what I love to do. Exactly what you're recommending is I like to study their own side more than them. I mean, just in preparation for our last debate here on
I'm going to send you I'm going to send the link right here.
I just went through an entire genetics course through Audible. I have another one on biology that I'll be going through over the next month. So I feel like, and so the point is the Michael Lynch lectures, we need to listen to those. As we continue refuting evolutionists, holding their feet to the fire, showing everybody why it's a great time to be a biblical creationist, it's great to know their own side better than they do.
You have
and
to.
then we know our own side much better than they do as well.
Yep.
Know their rescue devices, because yes, in most cases, and Sam and I have discussed this, in most cases, we're not going to convince the one we're debating. Why are debates useful? Why do them at all? You're not going to convince the debate. Well, you know what? It's for those on the audience. It's for those that reach out. It's for those that leave comments that, hey, they used to believe in evolution, or they've been on the fence, they're agnostic, but now because of these debates, now they're on the creation. So we're doing it largely for the audience so they can see that we have a defense for the faith, that we can counter these rescue devices, we can demolish their assertions.
We're casting down, strongholds, as Paul says.
Amen.
Tearing down every stronghold
and lofty thing raised up against knowledge of God. Yeah,
exactly.
All thoughts captive.
That's why I love being in the battlefield. I learn a lot. I think I learn the most, or close to the most, when I'm preparing for a debate or working on a project that's countering a critic, because now I'm forced and motivated to go see what they have to say, look at their side, dig deep on the issues. And every time I do that, I always come away feeling like I've learned a lot.
Yeah. And we're about out of time, but this is what I will leave. This is what I want to leave the audience with is, you're a creationist. The world is against you. That, most of the professors, everybody online is going to tell you you're stupid if you believe the Bible, or worse, you're deliberately deceiving people and all this. And so the deck is stacked against you. But I do want you to know that, for those of us that are willing to do the work and get prepared, do our homework, learn their theory better than they know it themselves, God is going to bless that kind of effort. He's not going to bless your effort if you just read a couple of articles, think you know what you're talking about, and then you think you're ready to go debate. No, it's going to end very badly for you. It takes years of study, highly in-depth. You need to be as or more educated on the topic than the PhD scientists you're debating. And if you do that, God is going to bless that effort. And God willing, it's always up to God, but God is much more likely, I think, to bless that kind of effort. And you can see what happened. I'm not a PhD scientist. I'm not a population geneticist, but I did my homework. I did the work. And I took on Dr. Zach Hancock, even when everybody was telling me that I needed to quit, and I was going to make myself a laughing stock. People like Grayson, he promised he would be there watching. He wasn't there, but he said, "Oh yeah, I'm going to watch with popcorn because you're going to make a fool of yourself." Instead, what happened? Zach Hancock took his paper, threw it in the trash, and ran away. Okay, so that's what happens when you do your homework. God's word is not going to be put to shame. God isn't going to be shown to be the one who's wrong. I don't care what kind of scientists you're talking to. They're not right if they're contradicting scripture. You can stand on that.
Wow, those are some powerful final words. Amen. Paul, I want to say these will be my last words, and Sam will get your last words. I want to say how thankful I am for you to step foot into the debate coliseum with someone like Dr. Zach Hancock, to spend what felt like 6 months as we worked out the details and scheduled the debate. You were the one willing to take him on and to take on the paper. And that's what we want to do here, is we actually want to address objections, address challenges, defend what we believe. And you did a great job, even in light of the fact that there was critics, as I was unaware, but critics like Grayson trying to discourage you. And where are they now? I think they know that they put all their hopes into that paper, into these novel arguments against genetic entropy. And now they've seen, and creationists have seen here, that those arguments don't work. So we've left no stone unturned here. Genetic entropy in 2026. Critics still haven't solved it. Regardless of the argument, synergistic epistasis, mutation count mechanisms, the infinitesimal model, you've debunked that here today. Zach and Dan's paper, an appeal to bacteria and mice, an appeal to truncation selection, all forms of selection. They don't work. It's a great time to be a biblical creationist, and the argument for genetic entropy is stronger than ever. Prove us wrong. The critics had their opportunity here tonight. They failed. I am going to go share this all around on social media, our Facebook page. I'm sure we'll get a ton of critics and comments there. We'll see if they can refute our arguments here, and perhaps one day soon we'll come back together if there are any worthwhile arguments and destroy those. So Sam, final words, final thoughts, brother?
Yeah, Donnie, thanks for having me on. I appreciate it. Paul, that was an awesome debate. Thank you for coming back and with this follow-up conversation. And yeah, for anyone out there, I guess the critics, if you are not an unbeliever for for emotional reasons, and you are interested in following the evidence where it will lead, well, I mean, these are powerful arguments that you've been given, and they should be taken seriously. So anyway, thank you again.
Amen. Praise the Lord. Paul, my brother, Sam, my brother, God bless you guys. Appreciate you doing this. Thank you for 2.5 hours of your time. To the audience, I hope you enjoyed this as much as I did. I enjoyed all the information. I'd recommend go back, especially after watching this, go back and re-listen to the debate between Paul Price and Zach Hancock. And just remember, it is a great time to be a biblical creationist. God bless you all. Standing for Truth is signing off.